Have you ever heard of a bee stopping its own message midway? Why does a bee suddenly stop dancing, but humans don't? What does a tiny bee know that humans still don't? What if a bee makes better decisions than us? If a bee realizes it's wrong, why does it stop immediately? The waggle dance was supposed to be pure instinct. New research shows the bee knows when her own message is wrong and stops. Humans, with 100 million times more neurons, rarely do. She comes back to the hive. She begins to dance. The other bees gather around her, reading the angle of her body, the speed of her waggle, the duration of her loops. She is telling them where the food is. And then, sometimes, she does something the textbooks did not predict. She slows down. She turns her body slightly. She stops dancing altogether. Mid-message. Why does she stop? What does she know that we don't? Here is what the textbooks say about honeybee waggle dance, how it works. A forager bee finds a patch of flowers. She returns to the hive. She walks in a figure-of-8 pattern on the vertical comb. The straight middle section, the waggle run, encodes two pieces of information at once. The angle relative to vertical tells the other bees the direction of the food, measured against the position of the sun. The duration of the waggle tells them the distance. A longer waggle means a longer flight. This was decoded by the Austrian biologist Carl von Frisch over decades of careful observation, published in his 1967 book, The Dance Language and Orientation of Bees. It won him a share of the Nobel Prize in 1973. For most of the 20th century, the waggle dance was treated as the cleanest example in nature of pure hardwired instinct. A genetic program, a behavioral reflex. The bee danced because she was a bee. End of story. That picture has been quietly falling apart for the last 15 years. Newer research suggests the waggle dance is not a fixed broadcast at all. It is a flexible piece of communication that the bee updates, downgrades, suppresses, and sometimes deliberately stops, based on information she has gathered, and based on information she receives from other bees. The dance is not instinct. It is a conversation. And the conversation, it turns out, has a stop button. What makes a bee stop dancing? Who taught her to do it? Here is what changed. In December 2011, a team led by Thomas Seeley at Cornell, along with collaborators at the University of Bristol and the University of California, Riverside, published a paper in the journal Science. It was titled, simply, Stop Signals Provide Cross-Inhibition in Collective Decision-Making by Honeybee Swarms. It is one of the most important papers in modern honeybee communication cognition, and almost no one outside the field has heard of it. The setup was elegant. When a honeybee colony outgrows its hive, it splits. A swarm of about 10,000 bees leaves the old nest and clusters on a nearby tree branch. From that cluster, scout bees fly out to look for new homes. A hollow tree, a cavity in a wall, the right kind of dark, dry, defensible space. When a scout finds a good site, she comes back and dances to advertise it. The longer she dances, the better she thinks the site is. The more she dances, the more other bees go to inspect it. Seeley and his team took swarms to a small treeless island called Appledore, off the coast of Maine. They set up 2 artificial nest boxes at equal distances from the swarm. They painted each scout be a small dot. Pink if she had visited one box, yellow if she had visited the other. Then they watched. What they saw had been hiding in plain sight for years. Scouts dancing for the pink site would deliberately walk up to scouts dancing for the yellow site, but them with their heads, and emit a short buzz lasting roughly 150 milliseconds. The targeted dancer would shorten her dance. If the headbutting continued, she would stop entirely. The team called this the stop signal. Bees were not just dancing. They were actively suppressing each other's dances. And the targeting was not random. A bee committed to the pink site almost exclusively headbutted bees promoting the yellow site and vice versa. The bees were doing something mathematicians and neuroscientists call cross-inhibition. Competing populations of evidence gatherers, each one suppressing the other, until one population reaches a threshold and wins. This is the same architecture at the same logical level that our own brains use to make decisions. The Seeley team modeled the system mathematically and showed it was nearly identical to what happens in monkey visual cortex when a monkey is choosing between two options. The swarm is a brain made of bees, and the dance is not pure instinct. It is a vote that the bee will withdraw the moment she learns better. What does it take to make a bee actually change her vote? What does it cost? Many people think the waggle dance is a kind of broadcast. The bee transmits, the other bees receive, nature takes its course. The research published in 2025 says something more uncomfortable than that. In November 2025, the French cognitive ethologist Martin Gerfa published a paper in the journal Trends in Cognitive Sciences titled The Cognitive Side of Communication in Social Insects. The paper pulls together more than a decade of evidence that pheromones, waggle dances, and other forms of insect communication are not fixed broadcast systems at all. They are cognitively plastic. The signal a bee produces depends on what she has experienced, what she has been told by other bees, and what she has updated her beliefs about since. The key finding is this: a bee that returns from a known good food patch and finds, on her next trip, that the patch has been depleted, will not just stop visiting it. She will actively downgrade her dance. She will shorten it. She will reduce the number of waggle runs. If conditions get worse, she will stop dancing about that patch entirely. Other bees, watching, will receive less recruitment to a place that is no longer worth visiting. A second bee, a scout investigating the same patch, can also produce a stop signal directed specifically at the dancer who is advertising it, if the scout has learned the patch is now dangerous. There is even evidence, going back to a 2010 paper by James Nee in Current Biology, that bees attacked at a food source will return to the hive and deliver stop signals to bees still dancing about it. The signal carries warning information. This means the waggle dance is not a sentence the bee says once and walks away from. It is a public claim she is willing to retract, downgrade, or actively cancel in real time in front of an audience based on new evidence. That is the part the news coverage almost universally missed. The interesting thing about the waggle dance is not how the bee makes a statement. It is how easily and how publicly she takes one back. Why are humans so much worse at this? What is the cost we pay that the bee does not? Here is the central question, then. If a honeybee with under 1 million neurons can update a public communication, downgrade it when conditions change, and stop transmitting it entirely when she has been proven wrong, what stops humans from doing the same? The answer is not that we lack the capacity. The cognitive operation is simple: receive new information, compare it to a prior position, adjust the position. Humans do this constantly in private. We do it badly in public. The cost of revising a publicly stated belief is, for humans, almost always social rather than cognitive. We have to admit in front of others that we were previously wrong. We have to interrupt the message we were broadcasting in front of the audience that watched us broadcast it. And we have to do it before the audience has stopped paying attention. The honeybee, by every measurable account, does this without any apparent cost at all. She stops mid-dance. She turns. She walks away. The bees who were reading her message simply update what they think about the food patch she had been advertising. Nobody loses face because no bee has a face to lose. The whole system runs on the assumption that the signal will keep changing as the world keeps changing. This is what swarm decision-making bees does that human institutions almost never do. Inside the swarm, there is no penalty for being wrong about the previous nest site. The bee who initially advertised it, then withdrew her support, is not demoted. She is not shamed. She is simply a bee who got new information and adjusted. The next time she finds a good site, the other bees will trust her dance again. We have built almost the opposite culture. In human institutions, the people who have publicly committed to a position pay the highest cost for reversing it, even when reversing is the right answer. So they hold the position. They keep dancing. The waggle dance on the comb in the dark is something humans have read backwards for most of a century. We thought the lesson was about communication. The lesson, it turns out, is about retraction, about the willingness to stop transmitting a message the moment you learn it is wrong. A bee can do this without thinking. We can do it only with a great deal of thinking, and most of the time we still don't. What would it take for humans to dance the way the bee dances? Why do we keep going when we know better? There is something to sit with here. The bee in the swarm is not modest. She is not wise. She is not, by any human standard of virtue, doing anything admirable. She is simply a bee in a system that rewards updating, run on a few 100,000 neurons that have no equipment for embarrassment. The dance changes because the world changed. The signal stops because the signal is no longer true. What is uncomfortable is that the architecture is available to us too. The Seeley team's mathematics show, in detail, that human decision-making circuits in the brain run on the same cross-inhibition logic as the swarm. We have the neurons. We have the evidence accumulation. We have, in principle, the capacity to listen to incoming information and quietly downgrade the things we previously said. What we have added is the social cost, the audience, the reputation, the career on the line. The bee does not have an audience. She has only nestmates who need accurate information about where the food is. She does not pay a price for changing her mind. She pays a much higher price, the colony does, if she refuses to. She stops because she knows. What other parts of collective intelligence have insects quietly figured out? Where else does the hive outperform the institution? The Cornell team's finding about the stop signal is part of a much larger picture about how honeybee colonies make collective decisions. A picture that closely echoes something a Roman emperor wrote down almost 2,000 years ago, without ever having seen the inside of a hive. Marcus Aurelius wrote a single line about bees that modern entomology has been quietly proving true ever since. What he said, and how the science of colony intelligence backs him up, is the next thing we will look at.